This is Math 151, and we're beginning Unit 4 on integrals, which is our third and last major topic in calculus. We started with limits, we've been working more recently with derivatives, and we'll now look at these integrals. In your textbook, this would be Chapter 5. In order to motivate the idea of an integral, you may have already completed a classwork assignment that helps you out with the idea of a Riemann sum. But in case you either aren't quite done or haven't seen it yet, I wanted to just share with you a little bit of background. The concept that we're after here is we're trying to find the area of some kind of a region that's underneath the curve y equals f of x. So my goal is to find this shaded area. The problem, of course, is that geometrically we don't usually have formulas unless our region has nice straight sides. Then we can use rectangles, triangles, trapezoids, or if we've got a circle. Other than that, we don't have good geometry formulas that allow us to find these areas with an irregular, curved shaped side. So what we're going to do is we're going to approximate these areas using a technique called Riemann sums. What we'll do is we'll imagine taking rectangles and coming as close as we can to filling up this area underneath the curve using rectangles. This particular one is called a lower Riemann sum because you'll notice all the rectangles lie underneath the curve. And this one's called an upper sum. You'll notice all these rectangles are slightly above the curve. Either way, what we're getting here with the area of the rectangles is just an approximation to the actual area of the curve. You can see in this lower sum we've missed little pieces. And you can see in this upper sum we've got some extra little pieces that don't really belong there. So in fact, these are estimates of the area. How can we make our estimates more accurate? Well, the more rectangles you use, the more accurate your estimates. Notice here we've got a lower sum using just 2 rectangles, and there's quite a lot of error, a lot of area that's not accounted for under our graph. Here's the same one, but we've now used 8 rectangles underneath our curve. And notice that the areas of these little pieces that have been left out are much smaller. Using 8 rectangles gives me a much better approximation of the area under the curve. So that's our goal, is to create these Riemann sums, which is nothing more than the sum of the areas of all of these little rectangles, which we'll then use as an approximation to the area under the curve. All right, so I'm going to start with a little vocabulary. Again, this vocabulary will probably make a bit more sense to you if you've had a chance to already take a look at that classwork sheet, but if not, we'll get there. Again, a Riemann sum is the sum of the areas of the rectangles used to approximate the area under the curve. If all the rectangles lie entirely below the curve, we say we're using inscribed rectangles. And in that case, the Riemann sum is often called a lower sum. It's a little too small, less than the actual area. If all the rectangles lie entirely above the curve, we say we're using circumscribed rectangles. And in that case, our Riemann sum is called an upper sum because our area estimate's a little too big. Sometimes we specify our Riemann sum by saying always use the left endpoint to determine the height, in which case I can have either an upper, lower, or neither one of those. And the same thing can be done by specifying right endpoints. In order to make our approximation using the Riemann sum more accurate, we can increase the number of rectangles used. And I'll just note real quick here, if I go back to this last picture, as we increase the number of rectangles, we also decrease the width of each rectangle. So we increase the number of rectangles, which also decreases the width of each rectangle. All right, in order to do this mathematically, to actually set this up and figure out what these areas are going to be approximated by, we're going to need a little bit of mathematical notation, which you may or may not have seen before, so I want to take a few minutes to review it. What we're going to need to use is what's called a summation. A summation is signified by the Greek letter sigma. It's a capital sigma, and it's used to indicate a sum. So for example, and let me make this just a little bigger. Yeah, that seemed really tiny. Whoops, where'd it go? All right, there we are. So, for example, the way to use the summation notation works like this. If I have the summation of the function 3i, and I'm letting the I values go from 1 to 8, what this tells me is to, in turn, let I equal 1, I equal 2, I equal 3, until I get up to 8, and add, sum, all of those terms. So this literally means 3 times 1, plus 3 times 2, plus 3 times 3, and so on. And I stop when I reach 3 times 8, that upper limit on my sum. And then I'm just going to go ahead, probably grab a calculator, and do all of that arithmetic. And when I did that, I ended up getting 108. Let's practice that one more time. Here I have the summation. I goes from 1 to 5. And my function is I squared minus 2i minus 2. So I start with 1, plus, I plug in 2, plus I plug in 3, and 4, and finally 5. And once again, you might want to just grab a calculator to do the actual arithmetic. When I did, I got 15 on this one. Notice several of those first ones are negative, which is why we got such a small value overall. So that's what a summation means. Now, this wasn't too bad because I had relatively small numbers to plug in, right? I didn't have to go from like 1 to 100 or 1 to 1,000 or anything. But if I did, if I had a much larger number of values to substitute in, this could be a really time-consuming thing to have to do. So fortunately, there's some formulas that can be used to help us out. They look like this. Our summation formulas say that if I want to take the sum as I goes from 1 to n of a constant, that's just adding c, n times. So I would get c times n. Seems logical. Take a look at this next one. The sum as I goes from 1 to n of I is n times n plus 1 over 2. This one's not real difficult to see, so I'm just going to take a little aside here and show it to you. If you imagine, for example, summing up the numbers from 1 to 100, this really means 1 plus 2 plus 3 plus 4 up to 97 plus 98 plus 99 plus 100, right? Think of this pattern. If I add 1 plus 100, I get 101. And if I add 2 plus 99, I get 101. 3 times 98, or 3 plus 98 is 101. 4 plus 97 is 101, etc. I'm going to end up with all of the numbers from 1 to 50 paired up with one of the numbers from 51 to 100. And each time the sum is going to be 101. So I'm going to have 50 pairs times 101 for a sum of 5,050. That's essentially an example of what this formula is doing. Notice that my original sum was to 100. N divided by 2, that's 50, the number of pairs. And n plus 1 would be 101. That's the sum of each pair. So that's just an illustration of why that formula works. The others are a little bit more difficult to actually see, but I will tell you mathematicians have definitely worked on these, so they're correct. If I want to sum the squares, 1 squared plus 2 squared plus 3 squared up to n squared, the sum is n plus 1, 2n plus 1 divided by 6. And here's the sum of all of the cubes, 1 cubed plus 2 cubed plus 3 cubed, and so on. The sum will be n squared, n plus 1 squared over 4. So let's go ahead and redo a couple, or at least one of the problems that we'd already tried, and see if we can get the same answer. Okay. Oh, and I'm almost there. It looks like I forgot something. My intent here was to actually redo this problem. I just forgot to type in the -2. So if you'll do me a favor and include that, I would appreciate it. All right. I'm going to start by splitting this up and saying I would have the sum of I squared minus 2 times, notice how I'm pulling that constant out of the sum. We've seen that a lot this semester. So minus this 2 times the sum of I minus the sum of just 2. I'm now going to use some of these formulas. To do the sum of I squared, I'll use this formula, and notice that my n is 5. So I would have 5 times 5 plus 1 times 2n would be 10 plus 1 over 6. Subtract 2 times. This is the sum of I, so up here. N is 5 times 5 plus 1 over 2 minus the sum of 2. That 2 is the c, it's the constant. So I'm going to get c times n, 2 times 5. So we've now used all of our formulas to get this sum. And again, at this point, I can just go ahead and grab my calculator and figure this out. Let's see, this is 6 divided by 6. Actually, that would go away. I probably don't even need a calculator. 5 times 11 would be 55. Minus 5 times 6 would be 30. Minus 10. 55 minus 40 is 15. So indeed, I do get the exact same answer as we did by writing this all out, using these formulas. Now again, is this saving me a lot of time? Maybe not so much, because I had a relatively small value of n, so doing it this way was pretty easy. But what if I have a much larger value of n? Take a look at this next example. I would like to sum from I equals 1 to 20, so a lot more terms. And goodness, I've got variable problems on this page. It should be a 2i cubed plus 4. So if I was going to write this out, I would have 20 terms to figure out and add up. That's going to take a lot of time. Instead, let's think of this as 2 times the sum of I cubed plus the sum of 4. that would be 2 times, and I cubed, I'm just going to go ahead and borrow this formula right here. Notice that in this case my n is 20. So we'd have 20 squared times 20 plus 1 squared over 4. Plus, this is just the sum of a constant. Our constant happens to be 4. So we get 4 times n, 4 times 20. All right, these numbers definitely are big enough to warrant a calculator, so let's do that. Let's see, I can cancel this just to make things a little bit less to type in. I'm going to have 20 squared times 21 squared divided by 2 plus 80. 88,280 is that sum. All right, so that's how you use that summation notation. I'm actually going to pause there because we're next going to start the whole idea of the Riemann sums, and I want to give that its own video.